Hiya, how you doing? Well, I hope you're doing well. I want to talk to you a little bit about complex numbers, but specifically about modulus and argan. I've got an interesting result to show you that will totally blow your mind if you've not seen this before, and it will also open up your eyes to how we can turn something that looks a bit difficult into something that's actually quite simple. All right. So I've just posed the question that if z1 is that, root 3 plus I, and if z2 is this, 3 over 2 plus 3, root 3 over 2i, then what is the modulus of z1, z2? And what is the argan of z1, z2? So you might think of the problem as, well, here are the two complex numbers, z1, z2. If you find the product of them, what's the modulus and what's the argan? Okay. Now, effectively, there's two ways of doing this. There's the quick way or there's the long way. If you're seeing this for the first time, you are going to do this the long way. So why don't we start doing that? Okay. If you've seen this before, then I don't know, maybe you'll fast forward this bit. I don't know, but keep watching anyway, okay? Because something interesting is going to happen if you're watching this for the first time. Right, so let's work out what z1 times z2 is, all right? So z1, z2, and of course we're going to multiply these two together, aren't we? So root 3 plus I multiplied by 3 over 2 plus 3 root 3 over 2 I. Now I'm just going to emphasise this is not the preferred method, this is the long way round. However, I need to do this, I need to go through this to show you what the quick method actually is. Alright, so let's go ahead with this. So you've got that times that, so that's 3 root 3 over 2, and then subtract 3 root 3 over 2, that's going to be 0, so that's kind of interesting, isn't it? And then the I terms, that's going to be that one, 3 over 2, and then this, so that's 3 times, so it's root 3 times, so it's 9, yeah, over 2, I, and let's simplify that, so it's 0, I'm not going to write 0, and then 3 over 2 plus 9 over 2 is 12 over 2, 6, it's just 6i, okay. Well, clearly then, the modulus of that is just 6. Let's write that down. So, mod of z1, z2 is equal to 6, and the argument is just going to be pi over 2, isn't it? Okay, so argument of z1, z2 is equal to pi over 2. So, how is it so? Let's just plot this on an Argan diagram, shall we? So, here's my Argan diagram, so real axis and imaginary axis. So the complex number 6i is just going to be there. So you can see the argument there, 90 degrees, pi over 2 radians. I'm using radians because it's the preferred angle of measure, and obviously just a modulus of 6. Okay. So you might think, well, nothing really interesting in that, is there? Well, let's just look at an alternative approach. Okay. Let's just go back to this, and let's consider what the modulus and argument are of z1 and z2 separately, shall we? That's what I'm going to do. So I'm going to write up here, okay? So modulus of z1, what's that going to be? We're using Pythagoras' theorem. That's going to be 3 plus 1, which is 4, square root of that, 2, okay? And let's do the modulus of that. So modulus of z2, so that squared is 9 over 4. That squared is going to be 27 over 4, yeah? Add them together, 36 over 4, which is 9, square root of that, which is 3. Right, so modulus of that is 3. Just want you to note that if you multiply 2 by 3, you get 6. Coincidence? We'll see. Okay. But if that was not a coincidence, if that was to work, wouldn't that be wonderful? Let's look at the argument of each of these. So argument of z1. So that's going to be 1 over root 3. So inverse tan of 1 over root 3, which is 30 degrees, pi over 6. Yeah. So pi over 6. And then argument of z2. So it's going to be that over that. The 2's will cancel, 3's. So inverse tan of root 3. Yeah. 60 degrees, pi over 3. Okay. And I'm just going to ask you to consider what you get when you add those two together. Pi over 6 plus pi over 3. You get pi over 2, don't you? Again, pi over 2. Is that a coincidence? Well, if not, again, that would be rather nice, wouldn't it? Okay. Right, what I'll ask us to do is just to bear those things in mind. Okay, bear those things in mind, and I want to show you another example to see whether or not this is coincidence. Okay, bear with me while I just clean up my board. Okay, so I've just cleaned my board. I've just summarised what we just had there. Okay, so we looked at Z1, Z2, these complex numbers. We looked at what the product of Z1 and Z2 was, then found the modulus and argument, and the answers were this and this. Separately, the modulus and argument of Z1 were this and this, and modulus of argument of Z2 was this and this. And I was suggesting that 2 times 3 equals 6, and that plus that is equal to that. And wouldn't that be lovely if that always worked? Okay, that was basically my suggestion, wasn't it? So let's just try it on another pair of complex numbers, because that's the thing to do, isn't it? Okay, was this a coincidence? Was it not? Let's just try out another pair of complex numbers. Okay, so let's just try it on those. And what we want to do is see if we get the same sort of results. So what we're going to have to do is work out separately the modulus and argument of Z1 and Z2, and then the product Z1 and Z2. Let's do it separately first of all. Okay, I'm trying to choose reasonably nice numbers so that we get, or so that the working's not too complex. Okay, too difficult. Okay, so I've chosen 3, 4 because, as you understand, it's nice and easy to get the modulus, isn't it? Okay, although you can choose any numbers you want. You can do this experiment at home if you wish. Just choose any numbers for complex numbers, okay, and then just see if the same result holds true. Okay. Right. So modulus of that is 5, and argument of Z1, well, it's going to be arctan of 4 over 3, isn't it? This is where the numbers unfortunately don't hold up to be as nice anymore, because there's no exact multiple of pi for arctan of 4 over 3. So I'm going to go for degrees in this one. It's just going to be a bit easier to see, okay? So that is 53.1 degrees, okay? Yeah. I've rounded it. Okay, it's 53.13 something. Okay, check it in your calculator if you don't believe me. But you know, this 3 plus 4 comes up so often. I've just seen it so many times. I just know it's 53.1 degrees. And then mod of Z2. So 1 plus 1 is 2. So the mod of that is root 2. And nice and straightforwardly, the argument of Z2. Well, that's going to be just pi over 4 or 45 degrees. I'm going for degrees in this one. Okay. So what I'm saying is, if my theory is correct, okay, I shouldn't really call it a theory, should I, in mathematics? What should I call it? Okay, my supposition, should we call it? Okay, if my supposition is correct, then I'm saying that the modulus of Z1, Z2 should be that times that, okay, and that the argument of Z1, Z2 should be that plus that, is what I'm saying. I'll leave it blank for the moment just in case it isn't. Right, we'll come back to that. So let's have a look. So Z1, Z2. Let's just multiply these together. So 3 plus 4i and 1 plus i. Okay, so 3 times 1, 3. 4i times I is negative 4, so 3 subtract 4 is negative 1. And then 4i plus 3i is 7i. Okay. Right, from that, we want to work out what the modulus is. So 1 plus 49 is 50. So you've got root 50. Okay. Mod Z1, Z2 is root 50. But hang on, I can simplify it as a third, can't I? That's going to be root 25 times 2, which is 5 root 2. And would you believe it? Look at that. It is the same, isn't it, as the product of those two numbers, 5 root 2. Okay, so my supposition was actually correct there, wasn't it? Okay, and then let's look at the argument of this, shall we? So argument of Z1, Z2 is going to be the inverse tan of, right, we're still going to do 7 over negative 1. I don't know that in my head. So I'm going to reach for the calculator here. So look, angle units, make sure I'm in degrees for this one. Right, so inverse tan of, what do I want? 7 over negative 1, so negative 7 equals negative 81.86. However, if I consider the Argan diagram, that's not where it is it? Okay, let's consider the Argan diagram of this. So the Argan diagram looks like that. My complex number is negative 1 plus 7i, so it puts it up there. Let's just label those. So that means that's the complex number there, isn't it? That's the angle I want. And the angle my calculator is giving me the negative 81. It's actually giving me that angle down by there. Okay, and I want this angle there. What am I going to do? well, I'm just going to add on 180 degrees to find it. And look at that, 98.1 degrees, okay, to one decimal place, 98.130. And would you believe it? It is that plus that, okay? It is 98.1 degrees to 3 significant figures, okay? So my second example I've given you also seems to hold true, okay? Does that now make it a theorem? Okay, does that make it true for all values? Of course not. What we've got to do is go ahead and prove this, okay? But it's a lovely result. And, you know, spoiler alert, yes, this does hold true for all complex numbers, okay? Isn't that fantastic? Isn't that amazing, okay? So I'm just going to emphasise what this means. It means when you've got any complex number now, Z1, any complex number Z2, to find the modulus of Z1, Z2, you just multiply each of these moduli separately. To find the argument of Z1, Z2, you just add the argument of that to the argument of that. And that's really, really helpful, okay? It can help us save a lot of time, okay? But why is this working? Why is this going to work? Okay, right, well, I'm going to show you, but first of all, let me just clean my board again. Okay, so my conjecture is actually true. I call it supposition. Conjecture is really a better word, all right? It's basically a theorem that when you have two complex numbers, Z1 and Z2, if you find the modulus of Z1 and Z2, you can just find the modulus of Z1 and Z2 separately and multiply them together. To find the argument of Z1 and Z2, you can just find the argument of Z1 and the argument of Z2 separately and just add them together. Okay, right, let's have a look to see why this is working. To do this, I'm going to introduce you to another way of representing complex numbers. Okay, so here's an Argan diagram with a complex number Z there. And of course, we all know that Z is generally represented as a complex number X plus IY. And I've used X and Y this time for a particular reason. Okay. Now, as you already know, on an Argan diagram, the coordinate XY will represent that complex number. All right. And what I'm saying there really is that this bit here would represent the real component, which we are calling X here. And this bit there would represent the imaginary component, which I'm going to represent as Y there. Now, when we find a modulus, we're looking at the length from the origin to the complex number itself plotted, aren't we? Okay, and I'm going to call that R. I call that R for radius, right? Radius of circle. And this angle there, when we find the argument relative to the positive x-axis or positive real axis, okay, then that's the argument there, the angle that this line here makes with that axis there, that's the argument, okay. Now, using simple trigonometry, when I say simple, I mean with right angle triangles, you can rewrite that, can't you? Okay, you can write that as R cosine theta, okay, because cosine theta is adjacent over hypotenuse. And this bit here, you can write that as R sine theta, because sine theta is opposite over hypotenuse, okay? So what that means is I can rewrite this. I can write the complex number Z as X, which is R cosine theta, plus IY, which is going to be R, how do I write this? Let's write it like this, R sine theta. Let's just put the I there, shall we? Okay, I'm a bit fiddly as to where to put that I in that bit. Okay, but what we're going to do is just factorise the R, factorise with the R, so what is R cosine theta plus I sine theta, okay? So you should be happy that Z can also be written as this. This is what we call modulus argument form, okay? This is what we call modulus argument form of a complex number. So what it is rather than write it in what you might call Cartesian form in terms of X and Y, we can write it in terms of the modulus and the argument only. Notice there's no X, Y coordinate position needed for the value of that complex number. Okay, so that's what modulus argument form is. Why am I talking to you about modulus argument form then? Well, it's to show you my result about the modulus and arguments before. I hope that makes sense to you. If you want to prove a result about the modulus and argument of a complex number, it's going to be far simpler to do it in what's called modulus argument form. Okay, right, hang on a minute while I clear my board yet again. Right, I've cleaned my board. I'm just going to take you back to this. Maybe those eagle-eyed of you spotted that I forgot to put an I in there, so I apologise about that. I'm going to fit it in now. What I want to do is just write these complex numbers in modulus argument form. All right, and I'd use his answers to do it. So Z1, written in the same form as I showed you, modulus argument form, would be R. Now what was the value of R for that? It was 2 for that, wasn't it? So the modulus of that was 2, and then open brackets, cosine, and then theta represented the argument there. What was the argument of that? It was pi over 6. Okay, so pi over 6, and then plus I sine pi over 6. So that is the same complex number as that, but just written in modulus argument form. And I'm going to do the same with Z2. Okay, so the modulus of Z2 was that, 3, and then cosine, and the argument of Z2 was pi over 3. So cosine pi over 3 plus I sine pi over 3. And if you want, that's just a nice example for you as to how you convert from the Cartesian form to the modulus argument form, okay? Now, what's nice about this is if you want to work backwards, it's really, really simple, okay? You just evaluate that. You work out cos pi over 6, times it by 2, and of course it gives you root 3. And you work out sine pi over 6, multiplied by 2, of course it gives you 1, hence root 3 plus I. And the same with this. Just evaluate that, expand the brackets, and you end up with this. So going backwards from mod arg form to Cartesian form is actually pretty easy. Okay. Now then, what happens when we multiply Z1 by Z2? Okay. Well, what I'm saying is that you'll get 2 times by 3, which is 6, and when you add the arguments together, pi over 6 plus pi over 3, that's pi over 2, and you should get this, I sine pi over 2. Okay, so that was what I was saying, that was what my conjecture was really. Okay, please don't call it the Brown conjecture because it's not mine. Far greater mathematicians than me came up with this. I'm just explaining it for you. Alright, so please, although I say my conjecture, it's not really mine, is it? Okay. So that's what I'm saying really, okay, that you multiply those together, you get this, and you add those together, you get that, okay. Of course, we worked out what Z1 and Z2 actually was. I can't remember it now, but remember, we did get the modulus of it was 6, and we did get the argument of it was pi over 2. So using those bits of information, that is correct. The modulus is that, the argument is that, okay. So modulus argument form, it's just a case of spotting what they are, multiplying them together, spotting what they are, and then adding them together. Okay. Now, if you remember the other example that I gave you, I'll just write that down now. That was 3 plus 4i, and that was 1 plus I. We do the same thing with that. Okay. Do remember that we got the modulus of that was 5, so that was 5 cosine. And then I worked out in degrees, didn't I? 53.1 degrees. So 53.1 degrees plus I sine 53.1 degrees. And then this was, modulus of that was root 2, if you remember. And that was cosine 45 degrees plus I sine 45 degrees. Just bear in mind that's rounded. Okay, so if you expanded the brackets and tried to get it, you wouldn't get exactly this because I've rounded 53.1 to 3 significant figures, okay? But if you remember, when we got the modulus of Z1 and Z2, it was that times that, wasn't it? Okay, 5 root 2. And when we added the arguments together, we got the same as when we worked out the arguments separately, the argument of Z1 and Z2. We got 98.1 degrees, didn't we? Plus I sine 98.1 degrees, okay? So what's the purpose of this, okay? All I've done really is just show you how to rewrite these complex numbers in modulus argument form. Well, the important thing is, I just want you to get a full enough grasp of this method of using complex numbers in modulus argument form before I went over the proof with you, okay? Because I'm going to use modulus argument form for the proof. Right, let me just clear the board, and then this is where all the exciting maths is going to happen, the proof of this result, okay? Okay, before I get into the proof, let's explain why I've got to do this particular approach. So from before, I started off with 2 complex numbers multiplied together, and if you remember, I ended up with the complex number 6i, didn't I? So what I'm trying to prove is that the argument of the first complex number added to the argument of the second complex number, okay, will give us the argument of Z1, Z2. So the argument of Z1, Z2 will be the argument of that plus the argument of that. So that being Z1, with theta1 argument, and that being Z2, theta2 argument, and I'm going to show that angle added to that angle gives us that angle there, which I could show you using a particular numerical example, but we've got to prove it works for every example, okay? And that the modulus Z1 times the modulus Z2 is going to be the modulus of Z1 and Z2. It's really rather difficult to do with just Cartesian form of a complex number. It would be so much easier if we can do it by comparing angles and the moduli. Hence this approach with modulus argument form. Now, any general complex number in modulus argument form can be written as this: r cosine theta plus I sine theta. So for two different complex numbers, we just need two different moduli, so r1, r2, and two different arguments, so theta1, theta2. So that gives me a general expression for two different complex numbers. So what we're after is z1, z2, and then the modulus and argument of that. So what we've got to do is we've got to multiply these together. So this times this. So r1 times r2, that's quite easy first of all, and then this bracket times this bracket here. So that's going to be cosine theta1 plus I sine theta1 multiplied by cosine theta2 plus I sine theta2. All right, and then we've got to expand those brackets. Okay. Now, I don't think I'm going to be able to fit this on one line, unfortunately. So I'm going to try and write it as best as I possibly can. So that's going to be equal to R1, R2, obviously. And because I'm not going to be able to write it on one line, I just want to emphasise the bracket here with R1, R2 outside the bracket. And if I expand these, I'm going to have that times that. So that's cosine theta1 cosine theta2, and then if I look at the real parts first, I'm going to multiply that by that. I times I, that's I squared, it's negative, so negative that times that, so subtract sine theta1 sine theta2. I'm only halfway through my expansion, so you can see what I mean by I'm not going to fit it all on. Okay, but that is the real component, all right? And now I can look at the imaginary component. So I'm going to put it on underneath here. So if I then add to that the imaginary component, so what's that going to be? So that's going to be that times that, isn't it? So cosine theta1 sine theta2, and then that times that, okay? So that's plus, and then sine theta1 cosine theta2. Close the bracket and close the large bracket. Alright, so all of that represents the imaginary component, all of that represents the real component. Okay, what do we do with that? We're going to have to make use of a trigonometric identity. Now, maybe you've seen these trigonometric identities, maybe you haven't. Okay, it depends on how far in the syllabus you've actually got. But let me just write down what they are. You can look them up if you wish. I'm not proving these identities, by the way. I'm just going to use them. If you want to see a proof of why these identities work, you go ahead and look that up. Okay. So the two identities I want to use are these, okay? I want to use identity for cosine A plus B and sine A plus B. These are called the addition formulae, okay? A plus B. Okay, there are double angle formulae and others, but these are called addition formulae for trigonometric identities. So this one here, first of all, that's cosine A cosine B, subtract sine A sine B. So if you're seeing this for the first time, notice that these brackets are not expanded in the same way you expand algebra, because cosine is not a multiplication command, okay? It's not a multiplication function. You don't just do cosine and then A plus cosine B. You don't expand brackets in the same way. So identity is that cosine A plus B in brackets is the same as this. Cos A cos B minus sine A sine B. And then sine A plus B, that's the same as sine A cos B plus cos A sine B. Okay, same again. Okay, it's not a multiplication function, it's a sine function, which is different. Okay, and that's the identity. Okay, I could use the identity symbol just to be mathematically more correct. That means that the left hand side is identical to the right hand side. Okay, I'm going to make use of these. So, what can I write this as? R1, R2, obviously, and then inside the brackets. Well, can you see how this one here can be rewritten? Okay, using this identity there, because you've got cos, cos, sine, sine, cos, cos, sine, sine, and it's minus, minus. Okay, can you see if I just write it with a and b instead, with theta 1, theta 2, that's the same as cosine, and in brackets a plus b, theta 1 plus theta 2. Okay, and then the I component, so plus I, and then can you see the identity I'm going to use here, that one there? So just don't worry about the fact that cosine sine are written the other way around. Okay, you can, obviously as a product you can write cos b sine a or sine a cos b. It's just that's how I memorise that identity, to be honest. Okay, sine cos, cos sine. It just helps me. It's the identity for sine something, so I start it off sine something. It's just my own logical way of thinking of trying to memorise it. Okay, but you can see that you're going to end up with sine theta 1 plus theta 2, because if I choose theta 1, theta 2 there, obviously you've got sine theta 1 cos theta 2, okay, which is that one there, and you've got cosine theta 1 sine theta 2, which is that one there. So hopefully you're happy it's the same. I'll just close off the bracket like that. Okay, and that is it. That's the proof. Can you see why that's a proof? It's because in modulus argument form we've ended up with z1 z2 is equal to that, which is the product of the two moduli there, r1 r2, and the addition of the two arguments, theta 1 plus theta 2. Okay, and hence your proof. Wasn't that lovely? Well, I hope you found it lovely. Okay, I hope you found some interesting bit of mathematics in there as well. Okay, yeah. So that means that for any two complex numbers, this is the proof of it. Okay, that when you multiply the two complex numbers together, the modulus is always going to be the same as the two moduli multiplied together separately. Okay. Let me just, it's always a shame to rub off a nice bit of mathematics, but let me just do that now. Okay, so what I'm saying is that in general, okay, if you want to work out the modulus of z1 times z2, to make it clear there, then that's the same as the modulus of z1 multiplied by the modulus of z2 there. That rule I've given you written in a more mathematical form with the symbols and notation. And similarly, if you want to work out the argument of z1, z2, you just add the arguments together. So the argument of z1 plus argument of z2. Okay, I'm hoping that you found that useful, but stick around, I've got a few more useful bits of information to go along with this. Okay, starting with this. All right, well, what if you instead divided the complex numbers together? What if you did a division? Okay, now maybe I'll leave that for you to go through in terms of the proof, but you can set it up in exactly the same way. All right, you have z1, z2, but then you write z1 divided by z2, and so you do all of that divided by all of that. Okay, it's just slightly longer, but not by much, but it's an interesting thing for you to go through. Okay, you'll need to do some manipulation of the expressions you get. You need to make a denominator real, okay, and you'll need to make use of the identities that are used for you. Maybe you can look up the alternatives. Just give you a hint, you'll need to look up cosine of a minus b, and you need to look up sine of a minus b. Okay, you need to find out what they are as identities. They're kind of similar, but I'll leave the fun part for you to work that out. Okay, and what results would you get, do you think? What results do you think you would get? You've got the time it takes, and just clean this part of the board to try and guess. Okay. There we go. Did you get it? Maybe you've got to pause the video to give yourself some extra time. Why not? Okay. No one's spying on you. No one's going to see it. Okay. So, what would happen if you wanted to find the modulus of z1 over z2? Of course, instead of multiplying the two moduli together, you would divide, wouldn't you? Okay, you'd end up with this result. Okay, that's clear to see. You just have r1 over r2 in your division. Yes, that's a nice and easy one to show. Okay, but what about the argument of z1 over z2? What do you think is going on there? Of course, instead of adding the arguments together, you're going to subtract. Okay, you'd have the argument of z1 subtract the argument of Z2. Okay, and what you'd be looking for in your proof is looking for making use of these. You'd end up with cosine theta 1 minus theta 2 and sine theta 1 minus theta 2 in your manipulation, in your expansion and simplification of Z1 over Z2. Okay, so it's another nice result for you. If you want, just practice to see how that actually works using your own complex numbers. Okay, I want to show you something else. Okay, now remember I've talked about modulus argument form, and of course I've talked to you about Cartesian form. Let me show you another way of writing a general complex number, okay, using what's called exponential form, though I sometimes call it Euler form, after, yes, the great man himself, the great mathematician himself, Leonhard Euler. Okay, so r e to the I theta, I'm not about to explain that one for you. Again, you can just research that if you want. But this is a third way we can write a complex number, okay. Let me just give an example of that. So, earlier I said one of the complex numbers was, I've rubbed it off the board now, I've got it written down there, so it was, I had a complex number and it was 2 cosine pi over 6 plus I sine pi over 6, wasn't it? Remember that? All that time ago? Well, the r and the theta just stand for the modulus and the argument, okay? So in terms of the Euler form, that would be 2 e to the pi over 6 I, okay? Which is a much simpler way of writing it, isn't it? Yeah, I'm sure you'd agree with that. And let me just rub this off a little bit. Do you remember, again, all the way back in my first example I showed you, I had another complex number, and in modulus argument form, that was 3 cosine pi over 3 plus I sine pi over 3. Yeah, and in Euler form, that is this. I'll just write Z1 there, Z2 there. That's 3 e to the pi over 3 I. Okay, so it's got its benefits using the exponential form, Euler form, okay, because it's much quicker to write down. All right, you don't need the cosine and the sine bit, you just need the r e to the I theta. Okay, now then, what happens when we multiply these two together? Z1, Z2, so that times that. Well, can you see the 2 times 3, it's kind of obvious, 6, but then you end up with e to the power of pi over 6 I plus pi over 3 I. Can you see that's what you'd do when you'd multiply these together? Remember, with indices, you do e to the power of this times e to the power of that, you just add the powers together, don't you? And of course that's 6 e to the pi over 2 I. Okay, that's just an example using numbers as to how that actually works. Let's just work out the proof then, using this Euler notation. Okay, so I can write this as, just write that off as well now that you know it, Z1 can be written as R1 e to the I theta 1, and Z2 is equal to R2 e to the I theta 2. Okay, let's see what happens when you multiply Z1 and Z2 together. You obviously get R1, R2, and then you get e to the, and then you add these together, it's going to be I theta 1 plus theta 2. Okay, the proof is much simpler, isn't it? Okay, despite the fact that it looks more complicated, more difficult, it's actually a lot simpler, isn't it? And you got it straight away, okay, in very little time. Okay, you got the 2 moduli multiplied together, you've got 2 arguments multiplied together. Let's do the Z1 over Z2 because it's very simple to do, okay, using Euler form. So Z1 over Z2, so that divided by that, so you got R1 over R2, and then you got e to the I theta 1 divided by e to the I theta 2. You'll subtract the indices this time, so you'll have I theta 1 subtract theta 2. Again, in almost no time at all, we've got the proof of it, okay? That Z1 over Z2, you've got to subtract the arguments, okay? I do love Euler form, and it's not just an excuse to mention Leonhard Euler, okay? It's just because it just makes things simpler, okay? It makes things much simpler, okay? I'm hoping that you enjoy that, okay? I'm hoping that I've given you something. I'm hoping that I've expanded your knowledge and appreciation of complex numbers. Okay, and I'm hoping that made your day generally. All right, I enjoyed it. I hope you did too. Okay, well, I'll see you again, and thanks for watching.